Bom, então acho que a gente pode começar, né?
Podemos?
Tá. Deixa eu só. Bom, boa tarde a todos. A gente vai começar o nosso seminário semanal com o Adamu Issifu. Ele é aluno de doutorado do Francisco. Por isso eu gostaria de pedir para o professor Francisco apresentá-lo antes. And he will talk in English, right? Francisco?
Okay, good afternoon, everyone. I'm not quite sure if Adamu can speak in Portuguese, but that's why I think he's choosing to talk in English. But I know that he can speak some Portuguese. Probably not enough to present some seminar. It's up to him. But anyway, as part of me, he was my student here in Campina Grande as a master student. And now he's finished his doctorate in João Pessoa, in UFPB. I'm also a member of the postgraduate program in João Pessoa. And now I'm finishing the work of Adamu with him. His thesis is almost done, and he's probably defending in July 31 or July 30. And this word is something related to effective models of QCD, as something he started with me in master thesis, and now he's getting more large. His involvement of this topic has begun very large, and he now attacking other problems like studying glueball, mesons, and other particles in this setup. So the effective models is very interesting because QCD, everyone who's working in QCD theories or particle theories or nuclear theories know very well that QCD is very nice to talk about large momentum transfer particles, but it fails in low energy momentum. So some people use QCD LATs as a way to get some informations. But effective models also have some room yet to compete a bit with LATs QCD, because there is a lot of problem that's not answered yet in LATs QCD. So effective glueballs, effective models are very welcome. So that's the problem. We started working in the master thesis of Adamu, and now he's developing more some issues in his PhD program in João Pessoa. So I believe he's ready to speak now. So that's all I have to say today. I leave Marcelo to start his speech. After that, Adamu will start his presentation. Marcelo, please, I think you can start.
So, all right. Thank you, Francisco. You may start, Adamu. Thank you so much.
Thank you very much, Marcelo, for your invitation to present part of our work in the usual weekly seminar in the physics department here. I'm much grateful, and I'm happy to be here again. It used to be my home, and I feel at home as well. So this particular model is centered on glueballs, and then the dual superconductivity that has been observed in the QCD vacuum. through lattice calculations and other phenomenological models. So basically, that is what the TCD is centered on. First of all, the background. We investigate glueballs and dual superconductivity using effective scalar force model. Our interest is to investigate the strong interactions that occur among glueballs. And we segment this study into two different regimes. That is the high energy regime and the low energy regime. In the high energy regime, we see high density particles annihilating and creating the same particles through the transfer of single photons. And then the low energy sector, that is where we look at the QCD properties such as the confinement and then the dual superconductivity. So we start with the scalar force model, and then the system undergoes spontaneous symmetry breaking through Abelian Higgs model to a low energy regime where we extract only the glueballs for analysis. So the scalar force undergoes some transformation as far as this model is concerned. Our theory, the theory for the model, are based on Dirac-Bond-Inford action. This action was derived based on the behavior of an open string on a D brane. So you imagine a single D brane with an open string, a closed string too on it. But to focus on our work, we decoupled the closed strings from the theory. So we concentrate on the open string. The motivation. Our motivation is the property of strings with their endpoints on a D brane. In this case, we could use their endpoints as the points that serve as the flux and sink of the color charge. That is because the QCD deals with color charges. So when we will deal with pure bosons, so we'll deal with glueballs. So here we would imagine that the valence glueballs are on the D brane, on the D brane, that's the endpoint of the string. Then the characteristics of the strings are tachyonic vacuum. There is something interesting happening to the open strings at the tachyonic vacuum. At the tachyonic vacuum, the D brane dissolves. So the endpoints of the string get connected through a flux line on the brane. And then the D brane dissolves to lower dimensional brane. So the endpoints of the strings contains the low dimensional brane. So here we have so here the endpoint of the brane, it will serve like a flux tube because of minimum energy principle. Because of minimum energy principle, it does not spread. The spring will behave like imagine rubber band, stretched rubber band, making it easy for us to determine the behavior of the gluons at the point. Now, the property of tachyons in quantum field theory is also one motivation. For the tachyons, we know that they are unstable particles with imaginary mass and stuff. But in quantum field theory, there's a nice way of removing this tachyonic mode. That is, you shifting the vacuum and expanding around the vacuum. In this case, the mass becomes positive, even though with some remnants of the brane, the mass becomes positive. So this is an interesting phenomenon. And then we're also motivated by the abelian dominance in low energy QCD. This has been proven in lattice QCD, in most lattice QCDs, which is almost considered as a precise physics now, that at the low energy, the string tension is purely abelian. And then we're also motivated by the symmetries of tachyon fields. particularly the Z2 symmetry, that allows it to go through the continuous symmetry breaking process, just like Higgs. So our objective is to produce color confinement from Abelian theory, and then to also present a technique that allows us to isolate glueballs for analysis, because what has impeded glueballs has been determined experimentally, but they are not affirmed because of the fear that they are mixed with pions. But in this model, you show how the pions are being swallowed by the Abelian gauge that we are going to introduce, leaving only the glueballs for analysis, and then that Abelian gauge becomes monopole, condensed monopole in the vacuum. Then we calculate Cornell-like potential. These potentials are very popular in QCD because they carry both the asymptotic freedom behavior of QCD and a confining behavior, and they are motivated by lattice QCD. Then we estimate glueball. We estimate glueball and gluon masses too as well from our model framework, and then calculate glueball and gluon condensate from our model framework. Then, when it comes to the color superconductivity, we study dual Meissner effect. Then we also calculate the superconducting monopole density, that is the NS, and the normal monopole that will be in the superconducting system. I will explain better when I get there. And then the London penetration depth, lambda. We calculate them, and then we study their behavior to at a finite temperature. So this is the Lagrangian density for the study. We have a complex scalar source. Here, the G here will be referring to it as scalar dielectric function, because it is actually the object that introduces the strong interaction that we need after the symmetry breaking. And this is the dual gauge field introduced. This will mediate the interaction at a high energy and then a potential. So this is the covariant derivative. And then the scalar dielectric function, it is important to note that it is dimensionless because of this Regis slope. So it will be dimension. The Regis slope has the dimension of a length square. So this is going to be length cube, which is going to neutralize the dimensions of the potential. But we set it to 1. This is very significant because the inverse of the Regis slope is precisely the string tension of the string in the brain. So this tells us that the string tension, we will be dealing with particles with string tension that is 1. And this is also a phenomenon that has been determined by lattice QCD. So this is the potential we are going to adapt. And then the third is complex. So we'll move on. We calculate the equations of motion. We realize that this equation 4 is nonlinear and difficult to solve in this regime. So we would not deal with it in this regime, but we deal with it subsequently. But this one can be dealt with through perturbation theory. And then equation 6 is simply, it looks like the Maxwell equation in dielectric medium. So we can calculate, we can determine this one, but we are interested in the static sector of the scalar source. So we choose only mu to be the spatial coordinate, that is 1, 2, and 3. We are working with spherical coordinates. And then we choose the charge density such that the current vanishes. Because we are interested in studying the confinement of electric source. So if the current remains in the system, it's going to create the scalar magnetic it is going to create some magnetic flux that will interfere the steady. So we truncate that and we deal with the charge density. Also, because the fields are static, the current will not also be generated. The scalar magnetic flux will be generated. So we also note that the Maxwell equation generates spherical symmetry even without torque. So this is constant, integration constant. Lambda, big lambda is the integration constant, which we relate it to the charge divided by 4 pi epsilon naught. This is a constant well known in electrodynamics. So determining the X matrix of equation 5, we have this, and then we can write the Feynman diagram for this in a 3 level. We have this. This shows that the particles annihilate and create through the exchange of a single photon. This is the high energy level. So to steady confinement, we shift the vacuum such that we can remove the tachyonic behavior from the spectrum of the potential, and then be able to study the observable we are going to get. So we shift the vacuum. We determine the true vacuum of the potential because it has a degenerate vacuum. We determine the true vacuum, and then we shift away from the usual field theory where we expand observable around their vacuum, which is 0. Here we are going to expand around the true vacuum in this way. So the potential will take this form. This field here, this new field here, we would be calling it glueball field because it's going to acquire positive mass. It's going to be acquired positive mass, and it represents a small fluctuation around the vacuum. As we know, this scalar field can be related to pions, physically, because pions are also bosons with spin 0 or integer spin, which can also be represented by the scalar field in nature. So we know that during the collision, the heavy collision in the Large Hadron Collider, a lot of pions are produced at the initial stages, and these pions, their flavor structure is surrounded by gluons. So as it cools as the energy decreases, these gluons also form bound states, which mix with the pions to sometimes form. You have a glueball pion mixing state, and then you have the pions coexisting with the glueballs in the system in that mixing form. So based on that idea, we can associate the small fluctuation to the glueballs that exist at that point. Now we want to go through the Higgs mechanism, break the symmetry. Already, this breaks the symmetry, but because we want to go to through the Higgs mechanism, we parameterize the scalar field in this form, where eta, as I said, is the glueball field, and then psi here is we associate it with the massless Numbo-Gosson field, or the pions, or what is popularly known as the Gosson fields or pions, light pions, which will represent small fluctuations around the vacuum. So, introducing this into the Lagrangian, we can decrease the Lagrangian to this form, where the Gosson bosons have been swallowed by the massive gauge field here, and then we can separate here. We can separate all the observables with glueballs in them, and then those without glueballs. Now, if we consider that at the highest glueball condensation, that is eta approaching 0, we realize that all the observables with eta will vanish, leaving just this equation here, the last two equations here. This one represents the monopole condensation in the vacuum, where you have strong confinement. Now, this is the transformation that actually takes away the Goldstone boson. Now, if we calculate the equations of motion of the Lagrangian after the symmetry breaking, we have these three equations here. This, as I said, the dual gauge field will represent the monopole condensation. This is the Maxwell equation modified by dielectric function. And then we can write the propagator for the glueball field. So with this propagator, we can quantize the glueball field. That will give you this quantization here. This equation will be particularly significant in our work at a particular point when we need to introduce the glueball fluctuating with temperature. We would just subtract the fundamental energy from this, and then we only have the number density multiplying this. So the number density transforms to Bose-Einstein distribution that introduces temperature into the system. We shall see that as we go on the presentation. Now, we realize that the electric field defined above, it is proportional to 1 over r squared. So when we are taking the static field, that is mu is going to be J, that is the spatial field, and then the mu is going to be 0. This is going to be precisely the electric field square. So when we put the electric field square, we have 1 over r squared, r cubed, 1 over r cubed. And then we assume that the particles are far away from each other, such that r cubed will be negligible. So we effectively decouple this one and deal with the rest of the equation. For here, we are dealing with equation 13. We'll get to equation, we'll also deal with equation 14 when we are studying the monopole condensation. So we get this Bessel function, which has this solution. In the solution, A has the dimensions of energy, but this alpha is the decay constant, the decay, it represents the decay of the pion, and it is dimensional. So we calculate the confinement potential using this solution into the electric field relation, and solving it with the electrodynamic potential. This is very common in dynamics. We get precisely the Coulomb-like potential that we set to calculate. Here, the m subscript phi squared is the glueball mass. So in effect, here we realize that we obtain Coulomb potential for confining colored particles, where the string tension is just a fraction of the glueball mass. Now, as we started, we said the string tension was going to be 1. As from the equation, we determined that the string tension was going to be 1 because of the Reggie slope that we set to 1. And then from this, when we do this, we can determine the glueball mass from here. So we realize the glueball mass is 1.73 GeV. This is precisely the value of glueball mass determined from lattice calculation 2. And from that, we can calculate the ratio, this ratio here, m phi over the square root of the string tension. This is also a well-known ratio in QCD at large end. That is the strong interaction between low energy machines. Then from this equation here, we can calculate the critical distance. This means that the particles, when they get to when you separate the particles to 1 centimeter, you should begin to see a clear confinement behavior among the particles. And we are going to buttress this with the graph for this one, for the confining potential. Now we calculate the effective masses of the system. That is the glueball, the thermal fluctuating glueball mass. So we take a thermal average of second differential of the Lagrangian with respect to the glueball field. So we obtain this. The gauge field, this is the thermal average of the gauge field. Also, in the future, we will need to use the thermal fluctuation in the glueball field. So we have defined that one here, which is the thermal fluctuation in the glueball field is equal to the mean glueball field. This is the thermal fluctuating term. This is the term that depends on temperature. So to avoid cross terms, we set a thermal average of the thermal fluctuating term to 0. And then we need to be able to know the behavior of this. We need to know the nature of the thermal average of the gauge field here. So we calculate it using third quanta distribution. This one can be calculated from the photon propagator. Can be calculated with choosing Fermat gauge and manipulating it. One can get this equation, and then this comes from the glueball field quantization. This term can be obtained from that equation. And then these are what we see here, E eta Ea. They are the dispersion relations for the glueball field and then the gluon field. And then this is the generic expression of the Bose-Einstein distribution function. So we solve those integrals in the high energy limit. We assume high energy limit. So we solve these integrals, and these are the results using the natural limit. So accordingly, we can write the thermal fluctuating glueball mass in this form. So we see that the glueball mass, they decrease with increasing temperature, and they vanishes at the critical temperature. And beyond the critical temperature, they attain negative mass. And this is a behavior that is seen in the quark gluon plasma regime, particularly the strong interaction quark gluon plasma regime. So we define the critical temperature. Here, what is significant here is that when there is no degenerate among the gluon cells, the critical temperature will go to infinity, meaning that all the glueballs are going to dissolve into gluons, into pure gluons. Now, knowing the dependence of the glueball mass on temperature, we can calculate the confining potential as a function of temperature as well, just by substituting the glueball potential in the equation, the glueball mass into the equation. And this is where we arrive at with the spring tension. So we realize that the spring tension actually breaks at TC critical. That is a thermal. At that point, we are going to have thermal hydronization. That is, the string is going to break, forming light fines in the system. That is instability. Also, after calculating all the observable depending on mass, we can also calculate the glueball potential as a function of mass, and that is going to take this form, meaning that the glueball, the glueballs also vanishes. The glueball potential also vanishes at the critical temperature and reduces as temperature increases. Now, we review briefly trace anomaly in QCD. In classical glue dynamics, the action is actually conformally invariant. And this leads to the creation of a scale current. And that scale current is related to the energy momentum tensor of the action in this way. But in the classical limit, the energy momentum tensor of the glue dynamics is 0, meaning that the scale current is conserved. At this point, the gluon condensate also vanishes. The gluon does not condense. Now, when one introduces quantum correction contributions to the theory, you realize that it becomes divergent. The scale current becomes divergent. That's because the energy momentum tensor is no longer 0. And then at this point, the gluon condensation do not also vanish. So this is what is termed as the scale anomaly in QCD, and this is because the classical symmetry, the symmetry of the classical action is not the true symmetry of the quantum quantum theory because of the quantum contributions that comes into the system. This is very important in two major ways in the standard model theory. That is, in the SU3, we would have axial, an axial current, we have an axial, we have singlet axial current, and that is generated due to this behavior, and that one carries an information. That is the 9th isoscalar meson is not an isoscalar Goldstone boson. So we see that we have 8 Goldstone bosons under the SU3 representation. That is the 3 pions, the 4 kaons, and then the eta. So the eta prime is not Goldstone boson, and that information can be extracted from here. And then the second one is an axial iso-vector axial current. That is also in SU2 representation. In fact, that is where the anomaly was determined. It is the process that leads to the discovery of the anomaly. That is where the neutral pion decays into 2 photons under that process. Now, with this, the vacuum energy density becomes negative. It's not 0 with the quantum contribution. And then the beta function that has appeared here is negative. This is very important in perturbation QCD, because in the perturbation QCD, this coupling constant is defined in terms of running coupling. That is through renormalization. So this tells us that as the energy in the system increases, the coupling decreases, and this is the consequences of the asymptotic free behavior of QCD theory. Now we also calculate the energy momentum tensor from our model framework, and then do an analysis of it. So from our model, we can calculate this as the energy momentum tensor. And then we rescale the bit shoulder, which I will refer to as the effective potential, because it's a combination of this and that. So we rescale it with the energy density at the vacuum. And then we rearrange, we can write this as a gluon condensate. So we realize that in the limit where the the vacuum energy density approaches zero, the gluon condensation vanishes. This is in line with the classical description. Now, from this, we can extract the gluon mass from the vacuum using this relation. And we compare our result with the standard form, which is obtained from Yang-Mills theory with the scalar force. So this the glueball mass, the scalar glueball mass, is as a result of the fluctuation around the scalar force that is introduced in the Yang-Mills theory to achieve this result. And this is the leading term in the low energy regime. So we know some theories have estimated the glueball mass, particularly the lattice QCD and some from electrical models. And then their masses ranges from 0.60 to 1 GeV. So knowing our glueball mass, we can slot our glueball mass here and then calculate the gluon mass, which is 0.787 GeV within the range that has been calculated from our model framework. Now, we express the vacuum in terms of temperature. In this case, we are going to replace all the glueball fields with temperature fluctuating glueball fields. So when we do that, the glueball field, in fact, if we take a thermal average of the equation of the Lagrangian after the spontaneous symmetry breaking, we realize that the glueball fields have two solutions. That is, they have 0 and then 1. And then the 0 means that you have higher gluon condensate in the system, because that is where you have higher glueball condensate when the ether field approaches 0. And then where we have higher glueball field in the system, we have a vanishing gluon condensate. That will also be clearer as we move on. So we choose the solution, that is the mean glueball field to be 1, and then we plot the triangle squared that was calculated up there in terms of temperature. This phi naught squared and phi naught squared, they are put here for a reason we know very soon. So, determining this critical temperature, we can calculate the vacuum dependent on only temperature. Here, at the critical temperature, it vanishes. The gluon condensate vanishes, and then the sign changes beyond the critical temperature, and that is the characteristic of quark gluon plasma phase. So we introduce this precisely to calculate the Debye-like mass. So when we take the gluon mass, the thermal fluctuating gluon mass from the vacuum in this form, setting this as the usual coupling constant that is seen in Debye mass, we get an expression that looks exactly like Debye mass, where the gluon mass increases with temperature. In fact, this is a regime where the critical temperature has been exceeded, as is captured in theory. So all the glueballs dissolve into gluons. So an increase in temperature is going to dissolve more glueballs and increase the gluon mass. So we compare our energy momentum tensor calculated with the energy momentum tensor calculated from glue dynamics, and we find that this term here is related to our scalar dielectric function. It's related to scalar dielectric function. So we can calculate the glueball, the beta function as a function of energy from our model. Now, the beta function is necessary because it shows the asymptotic freedom behavior of the system. That is, as we increase the momentum, the coupling constant rather decreases, and then the interaction of the particles reduces too. So to calculate the strong coupling constant, we compare this our equation for beta function to the standard one from the renormalization group theory. So when we express it that way, we can express it like this. We see that the strong coupling is precisely the scalar dielectric function here. So we can, if we can express this scalar dielectric function, the strong coupling and then the beta function in terms of space-like momentum or the 4-vector momentum and analyze their behavior. This strong coupling constant is important in QCD for the various reasons. One is that it helps to investigate the growing precision of hadron scattering at high energy limits, because at high energy limits there is little interaction among the particles. So that is where you can find the quark mass and other stuff. Yeah. And then at the low energy regime, it carries a lot of information too. We can analyze the structure of hadrons. We can study confinement among the particles, and then we can study hadronization. That is within the proton mass, 1 GeV. Now, we'll see why our beta function is necessary. This the gauge for the propagator is the spot is in the square bracket. That is precisely the photon propagator, which actually decouples at low energy or high wavelength. Meanwhile, at the high wavelength, that is the low energy regime. That is where the gluons and the glueballs are studied. So with this beta function, knowing that the beta function actually increases with decreasing momentum or decreasing energy, and then the gluon propagator also decreases with increasing momentum, it balances the photon propagator such that we can depict the characteristics of the gluon using this code. So in writing it, we use the Fourier transformation expressed down here. Now, in the limit where we have higher glueball condensation, as I expressed in the Lagrangian 11, all the terms with glueballs decouple, leaving the monopole condensation term. So we are going to use this to study our dual superconductivity. Now, equation of motion for this is going to be this. Then we are interested in studying the static force. So we write them, the static force. This is a dual Maxwell equation, and this is a dual Ampere's equation. And this is a Lorentz force, well known. And the Q here now becomes a monopole charge. It's a monopole charge. So to proceed with our analysis, we use our dual Ampere's equation expressed there, together with the dual Landin equation for persistent current by the monopole. When we use these two equations, we can come by this equation here, equation 54, which can be expanded here. Well, it is good to determine the Landin penetration depth in terms of our model. So knowing the expression for J subscript M, that is here, is going to be this particular term. We can use this definition to determine the Landin penetration depth, and that is going to be this in our model framework. So expanding this Laplacian here, we get this equation, differential equation, and we solve the differential equation in a spherical coordinate. We get this solution. We realize that the field decays exponentially. This is equivalent to the Meissner effect in superconducting, where superconductor where cells do not penetrate through the superconductor. In that case, the magnetic field inside the superconductor is 0. So applying a field, as with the Mesner effect, it does not penetrate. We have the same behavior here with the electric field. The electric field, it does not penetrate through the vacuum, giving it that behavior, superconducting behavior. Now we take the Maxwell's equation expressed above with the Landon accelerating current in this form. In that case, we use the continuity equation. We come by this expression here, which looks the same as the dual electric field there. So we find a solution to this equation, which is the same as the solution. And here, meaning the QCD vacuum does not allow the penetration of both electric field and a magnetic field. Now we calculate, we compare our Landon equation, the expression we obtained for the Landon penetration depth, to the standard form, which is this one, using natural field. So here too, we identify that the monopole charge here is equivalent to the electron charge in metal, and then the Cooper pair mass is equivalent to monopole mass here, also Cooper pair monopole mass here, and then the superconducting number density also can be identified with these parameters from our model. And this, we can express the fluxoid quantization relation. This is typical for type 2 superconductors, where in that superconductor where you exceed the lower field, that it has a lower and upper field. So when you exceed the lower field, you have some vortices penetrating the superconductor, and this is the quanta of those vortices that enter in the superconductor. So N is an integer, and then is the quantum of the electric flux. Now we can express, knowing that the glueball masses depends on temperature, and the glueball masses appear in the Landon penetration depth. We can express them in terms of temperature in this form. And then this is the superconducting number density, and N here is the total number of, is the density of total number of conducting electrons in the dual superconductor material. Here, in our case, it is going to be the total number of conducting monopoles in the vacuum. So we realize that here in the equation 54, when we set at 0 temperature, we have the Landon penetration depth to be equal to the Landon penetration depth at 0 temperature. Here we have a pure diamagnetic vacuum, which does not allow the penetration of electric and the magnetic field. And at T is equal to T critical, we see that the Landon penetration depth goes to infinity, marking the distinction between the superconducting phase and the non-superconducting phase. And at the T greater than the T critical, that is where the field lines go through the vacuum, just like the Mesner effect. So less than the critical temperature, the field will not penetrate. Now, Gotha and Casimir postulated in their theory that every superconducting material is made up of superconducting number density and then the normal electron density in this case, I'm describing it in terms of electron, and I'll apply it in terms of our monopole system. So, and all depends on temperature. So when you add these two, it should be equal to the density of the total conducting electron, which is N here. So using this as a guide, we can express this expression. Now here we can analyze this equation, the monopole number density. We realize that at T is equal to 0, that is when the superconducting material is cooled down to T is equal to 0, you have all the electrons conducting in the system being the total number of the monopoles in our case, the total number of the monopoles, conducting monopoles that's in the system. And then as the temperature increases, this superconducting monopole density decreases, keep decreasing. While now let's focus on this equation 66. You realize that as that decreases, as the temperature increases and the superconducting monopoles are decreasing, the normal monopoles also keep increasing, will keep increasing. So at a critical temperature, where the superconducting monopole vanishes, that is where you have the normal monopoles being at their maximum. This is determined in, they normally call it two-fluid system. But it is based on a superconducting material where they found that there was a normal current and there was a superconducting current that led to this analysis. So accordingly, the dual superconducting monopole, that is the NS, at temperature less than the critical temperature, conducts with dispersionless flow, while the normal monopoles conduct with finite resistance. This resistance may be due to interaction with the electrons with the lattice or pollution among the electrons that will reduce them. So at the lower temperature, their effects are not felt. So let's move on. Now the results. We realize from this that at the critical distance, that is 1. That is where we see the graph rising linearly. That is confinement. The particles get confined. And then this is the string tension. We realize that the string tension decreases sharply with temperature, and it breaks at the critical temperature, where we have the thermal hydronization. And then here is the Cornell potential as a function of temperature. So we realize that as the temperature, at 0 temperature, we have this. We have strong confinement. And as the temperature increases, the gradient of the graph decreases, showing that confinement is reducing. And at the critical temperature, you see, we have a thermal hydronization at that point. And this is the gluon condensate, the result for the gluon condensate as a function of the glueball frost. So we realize that at no glueball frost, where there's no glueball frost, we have the higher condensation. And at the maximum glueball frost, the gluon condensation also vanishes. Now, this is the glueball masses as a function of temperature too. They also decreases with temperature and vanishes at the critical temperature. We do not investigate the behavior at the temperature beyond the critical temperature, but at that is where you find the quark gluon plasma behavior, which we did not analyze in this way. Then we have the gluon condensation as a function of temperature. It also decreases with temperature and vanishes at the critical temperature. Then this is the Debye mass, the Debye-like potential we calculated, the Debye-like mass we calculated. So as a function of temperature, it increases with temperature. And then we have the glueball potential as a function of temperature. It also decreases. The glueball decreases as we increase the temperature of the system. Now, this is the landing penetration depth we calculated from our model framework. We realize that here we have a straight line. We have a straight line here. Where we have the straight line, that is the diamagnetic behavior of the vacuum. And here, where it starts rising, that is where we have the mixed state for type 2, and then the intermediate state for type 1 superconductors. And then this is the Massner effect exhibited by both the electric and the magnetic source at the vacuum of the potential. And then this is the behavior of the normal monopole number density, and then the superconducting monopole number density and the normal monopole density. We realize that at zero temperature, all the monopoles behave like superconducting monopoles, and then they start decreasing, while the population of the normal monopole starts increasing, and then they get to mix together at a point. This is the point if you are studying a type superconductor. This is the point where the vortices start penetrating the superconductor. And then when you keep increasing the temperature, the normal monopole density starts to dominate the superconducting monopole density. And at the critical temperature, the superconducting material will behave like a normal conductor, because all the superconducting monopoles will vanish, and the superconductivity will be destroyed. Summary: we have established that confinement of glueballs and dual superconductivity. We have established confinement of glueballs and dual superconductivity using Abelian gauge. After the spontaneous symmetry breaking, we observed that all the pions were swallowed by the massive gauge force, the dual gauge force, leaving only the pure glueballs for our analysis. Then we determined corona-like potential and its association with temperature. We determined the spring tension as a fraction of the glueball mass. We estimated the glueball mass and the gluon mass from our model framework. We also established that the dual superconducting phase occur at the confining phase. That is in the region where we have higher glueball condensation. And then we established a Meissner effect executed by both the electric and the magnetic source. And then we determined the superconducting monopole density and the normal monopole density, and then landing penetration depth, and analyze their behavior with temperature. Thank you for the opportunity to present my work before you.
Thank you so much, Adamu. So now we have time for some questions. You may write on the chat, open your microphone. So you may also ask in Portuguese, and I can translate to the speaker.
Oh, I understand the Portuguese. So anybody who wants to ask in Portuguese can ask, and I would
you can read in Portuguese, right?
Yeah, I understand, and I can even speak something, but I prefer to answer in English if the fellow can ask.
All right.
Eu não sei se os estudantes entenderam o que ele entende em português.
Sim, sim, ele entende português, vocês podem escrever em português.
Vou perguntar, abrir o microfone.
Também pode abrir o microfone e falar em português. So Adamu, what is your perspective now for your working after the PhD? It,
Okay.
did you already publish this work?
Yeah, this work is in archives. We have submitted it to a journal. It hasn't been published, but there are others of its kind that has been published. And then what we intend to do is that there are so many things we can do with the theory that we haven't done. For instance, we can, with availability of a computational artifact, we can discretize these equations and then study them in the lattice PCB. Another thing is that the corner potential is a potential for heavy quaternion system that has been established in lattice PCB. So what we intend to do is that we are going to fit our potential into the quaternion spectrum. The spectrum is not complete yet, so we are going to fit it in and make some predictions for the part that has not been calculated yet. We intend to do that. And then another thing is that this theories could be used to study cosmological stuff, such as
Cool. I was thinking just about this. What kind of other applications in
this
cosmology?
particular. This yes, it is in terms of this particular model. The Lagrangian here, we can use it to study the evolution of the early universe. When we integrate out the gauge field to serve as radiation correction to the potential. In that case, we have an effective potential that can be used to study the evolution of the universe through
For
series of
something
phase
for
transitions.
you think something for dark energy?
Yes, we could. We could.
Yeah, cool. And for later in universe for inflation. What do you think?
Yes, this can be used for to study inflation through phase transition. I think there is some work between myself, Professor Francisco, and one of my colleagues, Julius Caesar, using a model like this to study the inflation of
And
the
for
early universe.
astrophysics, because the superconductivity is a phenomenon which may happens in compact objects like
Yeah, neutron stars,
white dwarfs, neutron stars. Yes,
neutron stars.
cool. Thank you.
You're welcome.
Mais alguém tem perguntas?
Eu vou fazer uma pergunta em português para os alunos se estimularem a fazer pergunta.
All
Adamu,
right.
Yeah.
você pode explicar melhor o que é dual superconductivity? O que é dual o que é supercondutividade dual para os estudantes?
Okay. Superconductivity is simply a material that conducts with zero resistance, without resistance. Many materials can do that, but for now, what is being studied is that when the material has to be cooled below some critical temperature before it starts exhibiting that behavior. And within such material, such material, the magnetic field or the magnetic conduction, as it is said, is zero. Is zero. So when you apply an external field, when you apply external field and the external field is removed, it doesn't get magnetized. It goes into its original state. I think that is what I can say about that. Unlike a perfect conductor where you have a constant magnetic field inside, right? So with the, if you apply a force, external force, the force goes through it. And then when you remove the external force, it gets magnetized too as well. That's the superconductor. So that's the difference between the superconductor and the superconductor.
Para aqueles que conhecem supercondutividade, acho que não teve grande dificuldade de entender supercondutividade dual. Né? Essencialmente, você está trocando os papéis entre partículas supercondutoras, né, e monopolos supercondutores. Né?
Yeah.
Na QCD, você tem esse papel trocados. Né?
Yeah.
Então, acho que quem entende supercondutividade deve ter entendido bem o tema. Agora, se não conhece ainda o assunto, acho que quem conhece mais o assunto de supercondutividade são aqueles de matéria condensada, né? Eu não sei se tem pessoas aqui de matéria condensada, eles sabem muito bem o que é supercondutividade eletrônica, digamos assim, em metais.
Yeah.
Essa supercondutividade em ambiente, que você tem matéria hadrônica, né, que são partículas como glueballs ou mesons, isso é invertido, né? Você troca os papéis, né? Então, ao invés de ter uma corrente de elétrons, você tem uma corrente de monopolos magnéticos. Então, Adamu, isso aí é mais para os alunos, tentando explicar para eles um pouco em português. Ok? Então, não sei, se ficou mais claro para eles ficar mais à vontade para perguntar ou não sei. Às vezes ninguém quer perguntar mesmo, porque está com vergonha, ou de saco cheio também.
Sem mais perguntas? Bom, então acho que a gente pode encerrar por aqui. Eu vou pedir para que vocês abram o microfone para que a gente possa agradecer com aplauso o palestrante. Thank you so much, Adamu, for your good presentation, and I'd like to wish you luck on your last year in PhD last year.